Hi, welcome back. So previously we mentioned about uh, the Joule's law and how internal energy is a function of temperature. If the temperature does not change, it means that the internal energy of the gas does not change as well. Alright, so and then we went about to look at example 4.2 and see how we can calculate for the change in internal energy. At section 4.3, okay, we introduce you to the diagrams, okay, the PV curves, as I would like to say, and the 5 processes that this chapter is going to concentrate on. Okay, the 5 processes are namely constant temperature, constant pressure, constant volume, adiabatic, and polytropic. Okay, I can just start from constant pressure first. So remember when we had this equation P1 V1 over T1, P2 V2 over T2, it means that when the gas, right, the gas in the system goes from one state to the next state, okay, it has a certain pressure, volume, temperature, and it goes through a process to reach another pressure, volume, and temperature. If this process, okay, is the so-called constant pressure process, it basically means that from state 1 to state 2, the pressure does not change. It means that P1 is actually equals to P2. What will happen if this happens? You can actually see that this equation gets simplified, okay, to become V1 over T1 equals V2 over T2. Okay, if I reorganize it again, it becomes V1 over V2 equals to T1 over T2. Okay, looking at this equation, it is instinctive to know that if the volume increases, the temperature should also increase, if the pressure stays the same. Okay, so this is a linear relationship and direct linear relationship. Okay, and it is also stated over here. Okay, this should be 2. Sorry, dear. Okay, the relationship with this one, right, I can also bring it to a, so let's say V1 over T1, V2 over T2. As long as all the processes are constant pressure, you can just keep on making the same expression like this. Okay, means that these will always be the same. The same meaning it will always be constant. Okay, that's why here it says that V over T is a constant. Okay, and with this you will be able to derive the unknown values depending on what is given to you in the question and what is not given to you in the question. Okay, in the PV curve it will look like this. Okay, because it's constant pressure, the pressure does not change. P1 equals to P2 and it will be a straight line across. So you will see that this is state 1 initial, this is state 2. Okay, in a PV curve, why is this shaded? Because the work done is generally the area under the process. Okay, if this is my process, the area under the process will be the work done. This, by integrating this area here, will give you work done in joules. Okay, so this is the idea behind, and using this, right, the rest of the page of this section just goes about to derive the expressions for you. Okay, how do you find work done? Okay, basically it's just my pressure multiplied by the change in volume, so that will give you the work done. Okay, and because of that, and knowing that delta U is this expression, you can actually use the first law, right, to get the expression for Q. Okay, so this is what we will be doing for the next for the next 4 processes. Okay, at the end of the day, you will get what is shown on page 67. Okay, this is a table which pretty much summarizes all the 5 processes, one row for one process. Okay, constant pressure, constant volume, temperature, polytropic, and adiabatic. And for each process, what are the equations that you can use in terms of the equation of states? Okay, and how can you find the change in internal energy? How can you find the heat gain or heat loss? How can you find the work done? Okay, this table will be given to you during the exams, but you need to practice more, okay, so that you know how to use this table. Not all the equations are inside. For example, PV equals MRT is not here. Okay, and there's also another equation, if you remember, which I mentioned to you about specific heat capacity. Okay, so let's look at this one as well. On page 57, there's a description on relationship between the gas constant, Cp, and Cv. Okay, and you will get this expression. Cp minus Cv is equals to R. Okay, this a lot of times you need to use. Sometimes 2 of them will be given to you and you need to find the third value. Okay, any 2 of them, with any 2 of them you can find the third value. Alright, so yeah, this is pretty much the summary. Let's go through the example 4-3, okay, to show you how we can make use of the formula tables behind. So now, so the gas has initial properties such and such, undergoes a constant pressure process, right, to a temperature. So this is the final temperature, T2, 120 degrees. What is the heat, Q, and what is the work done, W? The R is given, Cp is given, so Cv you should be able to find. Okay, so let's just list out everything here first. P1 is 250,000. V1 is 0.5. T1 is 330 Kelvin. Okay, this is meter cube, this is Pascal. And you know that T2 is 120 plus 273. This gives you 393 Kelvin. Okay, and you know R is 288 joules per kilogram Kelvin. Cp is 1007. So Cv is Cp minus R. .719. Okay, this is also joules per kilogram Kelvin. This is also joules per kilogram Kelvin. Okay, so then you turn to the formula table. Okay, the question asks for work done and heat transfer. So the work done for constant pressure is MC, no, this one. Okay, MR T2 minus T1 or PV2 minus V1. Okay, you need to look at what are given to you, which properties are given to you, and which formulas you should use more efficiently. So I think instinctively you have temperatures, you should be using the second formula over here. Okay, so my W is M R T2 minus T1. Alright, but first we need to find M. We need to find M. We have P, V, T, and R. We can find M first. Okay, so M equals to P1 V1 over R T1. Okay, 0.5. R is 288. T1 is 330. Okay, this will give you 1.315 kilogram. Okay, so with this mass, you can put inside 1.315. R is 288, and the change in temperature is 393 minus 330. Okay. (23) 23863, which will be 23.863 kilojoules. Okay, so this is how you use the formula. Next is Q, is MCP T2 minus T1. M we already have. CP we find it to be 7. No, CP is 1007. Okay, and T2 minus T1. You should get 83.44 kilojoules. Alright, let me just multiply here. Okay, you'll get 83424, which becomes 83, about 83.4 kilojoules. Okay, so this is how you approach a typical problem, and we'll go to the next process after this video.